The setup window, you should see your mesh with the different zones labeled in different colors, and you can control how these colors look somewhere in here using display. It just made my pour wall the same color as the other walls, but at least the inlet, outlet, and axis have different colors. And it doesn't really matter, but it's kind of nice to see that your named selections came through if they're different colors. We have to work our way down through the things on the side panel here. Just like usual, they make you work through these step by step. In scale, that's the most important one for us, and kind of the weirdest thing that we have going that a lot of these examples don't is that we're at the micro scale. And being that units were in meters, in my input file, I have something that's 0.2 meters and then the minus x, 0.2 meters and plus x is 0.4 meters across. I don't really mean that. I want it to be 0.4 millimeters. I want it to be like 400 microns for this whole span right here. So we have to scale it, and we can do that 0.1, scale in both directions. And each time I click scale, it's going to multiply by the scaling factor that I just typed in. And the best way to look at this is use the domain extents. I know I'm trying to get down to 0.4 or 0.2 for the minus and plus millimeters. I scaled it once and I've moved it over by one factor of 10 in that direction, getting it smaller. So I keep applying. This is the thing that threw me the first time, and I've got another factor, and it's like how many times I click the scale button. So what I'm really looking for here is to get this down. I'm at 2 millimeters, but I want to be at 0.2. So 2 millimeters is 2 thousandths of a meter. So I'm going to scale it one more time and put that over there. And then I'm going to get my domain being 400 microns across. And it's also taking the Y thing in the same direction. If you went too far and screwed it up, you can hit unscale and get back to what you started with. Okay, hit close on there. We want to have a pressure-based simulation. I'm using an incompressible fluid. Absolute velocity has been fine, steady. Yeah, we want to look at this thing in steady state. It's going to be a closed container with, we're going to put a wall speed on this thing, kind of like this wall is constantly moving this way to represent electrokinetic flow driven at this wall right here. And everything else is closed up. And we're going to look at that after some time, so it's steady state is built up. The thing we have to change is make it axis symmetric. And the units as it came in are usually fine. Okay, and then we can move our way on down. This one's already looking good. We want to have everything off, but viscous laminar, we're going to look at laminar flow of an incompressible fluid. The materials pane, now this one we have to modify. We want to have water, and since we chose viscous laminar, okay, we can hit that air that it defaults to for the material in this green area and edit that and make it more like water. Okay, let's bring this into the place you can see it. And since it's such a limited simulation, we're not doing thermal transfer or compressible things or anything. We just have to enter the material's density and viscosity. And you can look through the Fluent database and find these things for water. I'm just going to change this name to water. And then I'm going to change, now I got to fix this. So I got these numbers right out of the Fluent database. I didn't have to go hunting around for them very much. And then have something for liquid water, 998.2 kilograms per cubic meter. And this other viscosity, 0.001, oh fine, 003, I'm sure that matters, kilograms per meter per second. And now I'm going to do change, create, yes, and overwrite error. I didn't change error in the whole Fluent world for everyone. I changed it for my simulation. Okay, close. And I could have called it anything. I could have called it syrup or whatever. And as long as it's got the viscosity and density, then we're good. Cell zone conditions. I don't have to do much there. What I do have to do is boundary conditions. And the one that I have to edit is the pour wall. I need to go in here. Oh, everything's shifting a little out of sight, moving wall. Okay, and in an add-on to this tutorial, what I'd like to do is add a non-uniform velocity, but right now, let's just put in something in the X direction this way, horizontally. Okay, we got to see that in the meshing panel that X was this direction. And so our vector for this direction is going to have 1 for its X component and 0 for its Y component. And speed, let's put it at a millimeter per second, 0.001. No slip in translational. And, well, we don't really have moving cells on it, but we can put absolute. Okay. And that's the only thing we have to do. We can look at some of the other ones. That's the green stuff. Let's look at the inlet. Just to be clear, the inlet is not moving. There's no velocity on the inlet wall. And that's kind of unusual, but it is representing a closed container. Usually people will have a inlet flow that's coming from maybe some other simulation or just some conditions that they want to set up in a wind tunnel or something. Okay, and then so I can move on down. Dynamic mesh, don't really do anything with that. Reference values, we don't really do. Solution methods, we're doing a lot of defaults on these things. Solution controls, default. Residuals, here we have to change something. Let's edit. Residuals. The important thing here, and this sounds horrible when you first hear about it, residuals are telling you how well your solution is doing at converging. How does the solution, this iteration, differ from the one last time? And eventually, ideally, those solutions are stable, and we're looking for one iteration to be very similar to the next. And then we know it's not changing very much, we're close to being done, and we check that convergence. Let's see if I can bigify this. Maybe not. Let's check convergence refers to this column and right here. Whether we'll talk about X velocity, Y velocity, or continuity. But if we check convergence at this microscale, it thinks it's done right in the beginning, no matter how small I make this. And I don't know why, but what people do in the forums is uncheck this and just make it iterate a lot. We're still going to watch whether it's converging, and these residuals should get smaller and smaller. And then that's a very important thing to change. Initialization, hybrid is what it defaulted to, and I just stick with that. Calculation activities, don't do too much there. Number of iterations, let's put 500. And then calculate. The solution must be initialized, yes. Calculating solution. Oh, good. And these are the residuals, the difference in X and Y velocity from one iteration to the next as it goes on. And it's gone up to about 100. I put 500, which might be a little bit excessive, but these residuals still keep getting better. They haven't really stabilized. They're just going farther and farther down. But we'll be here a while. Hopefully I can store this video and you can watch it. And running on a computer. It's not running on the MacBook. It's out somewhere in the wild running on this parallel processor, and still it's taking its sweet time. The good news about this is if you put something more modest, like 200 iterations, okay, we'd be done already, but next time you pick up, if you want to do more iterations, it's not going to throw away the old solution. It's just going to start where it stopped. So if you stopped about here, it would keep all that stuff, all the velocities in each cell. But finally, we're done. And the fun part, graphics and animations. Let's look at the velocity vectors, and this is something where it's a very common task, so the defaults are usually pretty good. Let's hit display. And it's very small.